So like today I'ma just tell you how to implement a linear layer in pure Python, no NumPy, no nothing. Linear layers, also known as fully connected layers, are actually a form of, it's a layer of course, but it takes in an input vector and outputs a vector. It's one of the most basic layers out there and it's the easiest to implement. It's not that bad, but the basic formula for it is y equals my keyboard. I have a faulty keyboard. One of my squiggly bracket keys don't work, okay? This is gonna be a bit of a pain in the ass, so we're just gonna have to do this the best way possible. So in this situation, y is the output vector. Hold on, I'll make a little log here. Y equals output vector. W equals weight matrix, which is literally just the weights. B will be the biases, and X will be the input vector. So the basic formula for a linear layer is this, which literally means the output is the weights times the input plus the bias. It's so easy you could implement it on a calculator. It's fairly handy. Yeah, here we go. So it's so easy to implement. You can pure Python. Here you go. This is Cursor, an IDE. It's a modified version of Visual Studio Code with language models built into it for assistance, kinda. But I'm gonna use it because again, one of my keys are broken. I could have done this on my laptop. My laptop's too dinky to handle this type of video, even recording at the same time. Yeah. So, just as a start, we'll define the linear layer. Yeah, so you need this, right? But we're not gonna use NumPy at all because NumPy is heavy. So we're gonna have to define the weights as, oh snap, the key doesn't work. I'm gonna have to come up with something. Hold on. God damn it. There. Gotcha. I'm gonna just have to leave this on my clipboard, I guess. So we're gonna have to do. Yeah. No. That's not what I wanted. Import random. No. So we're gonna, yes, random. I'm gonna turn this off for now. Disabled. There we go. So we're gonna do uniform. It's disabled. There we go. 0.1. 0.1 for in range input size for in range output underscore size. So even just if we test it for now. Let's just set this as 2 and set that as 2. Let's just print out the random weights and see what they come up as. You see, right here. Those are 4. Well, yeah, you need 4 sets of weight. Well, 2 sets of weights for each input and output. But so now for the biases, it's much. Okay. For the biases, it's self.bias equals. It's a very similar thing, but you only do it once. Uniform. 0.1, 0.1 for in range output underscore size. That's all you need for now. So now we can also test this out by, there we go. Let's see what this looks like. Now, the thing is though, since all these models are, their weights are randomly defined, it does sometimes help them to learn like quicker. But this does mean that it's not as reproducible. I'm pretty sure random.seed, yes. I'm going to set my seed to 42. As you see here, they're going to be both the same now for this. So it's going to be the most reproducible thing ever. 42 is a funny number too, because for some reason it's the most used number for seeds. And funnily enough, it's like the number 42 is the answer to life, the universe, and everything, or something like that. But yeah, it's super random. So we're gonna do self. Yeah, that's right. Output equals. So we're gonna set the output to be an empty array for I in. Well, hold on. Let me try to do this as neat as possible for each underscore weight in range len self dot weights. We wanna the dot product. The dot product is everything total together. That's fairly easy to do though. So we want to get the dot product equals sum self dot weights wealth self dot weights oh yeah, each underscore weight. But now we're gonna get the sub value of each weight, kinda. So what we're gonna do is we're gonna just, let's call it J for now. J easiest for J in range len x. And that's the dot product. And then if I just output dot append dot product plus self dot bias and each underscore weight. That's the simplest part of it, at least. But if you really want a simple example, this is already quite clear. So for each weight in the range of weights, you get the dot product of the input plus the weight, kinda. And then you append that to the output. That's the most minimum. As you can see here, let's just set x to 5, 6, 8, 7, 8, yeah. And then we're gonna linear dot underscore layer dot forward x. Oh, I haven't returned the output. What am I doing? Output. There. You see, that's the dot product for us, I guess. That's the output. But the input size isn't matching, as you can see here. So if we do this, do we want to condense it to 2? You know what? Sure. As you see here, these are the inputs. These are the total amount of weights. These are the biases. And this is the total output. Um, and that's the simplest implementation of it. This is after I recorded the video, but you should always check shapes before you input stuff, because it can cause some issues if you're training and the input sizes are wrong. Okay, thanks.